AnyLogic as a simulation platform for applied AI. I'm Arash Matavi. I'm the AI program lead at AnyLogic North America. And with me is my colleague, Tyler Wolf-Adam. He's a simulation modeling specialist in our office in North America. We planned a lot of topics to cover for today. Just an overview of what you will see in this presentation and workshop would be an introduction to simulation modeling, knowing that almost all of you who are joining us in Winter Simulation Conference are experts in simulation. We're just going to go through a very brief introduction to what this software and AnyLogic ecosystem has to offer. Then I will show you a few examples of AnyLogic and AnyLogic Cloud, and I will point you to other workshops and vendor tracks, vendor tutorials that we'll have in the following days. So if you need to get more information or interested to learn more about AnyLogic and AnyLogic Cloud and the future and the roadmap of AnyLogic, you can get more information. Then we talk about the the differences between the simulation and artificial intelligence in general at conceptual level. And then we get to the main topic of the workshop, which is the intersection of simulation and AI. And we cover it in three main categories of intersections: when we are generating synthetic data and use it for AI purposes, when we use simulation modeling as learning environment for reinforcement learning, and when we use simulation as a test bed to test AI solutions or trained models. And at the end, I will point you to some extra resources in case you wanted to follow up and try some of the technologies that I'm going to introduce you to in this workshop. Okay, so let's start by a brief introduction to simulation modeling and what we are covering here. At very high level, if you are new to this concept, which I'm kind of doubted because you're in Winter Simulation Conference, but in general, the main idea for any type of modeling is to move from the real world to the world of models, which is a risk-free world, do all of our experimentations and tests in this risk-free world, and then we are happy with the solutions that we are identifying or uncovering, deploy them in real world. So that's the main, basically, workflow instead of going directly from a real system in its current state into a modified version and just observe the consequences of changes live in real world. So that's the main idea. Okay, so that was about all types of modeling approaches, but we are focusing more on simulation. What gives simulation this uniqueness and usefulness is that simulation is a prospection technique. Basically, it gives you this insight into the futures or possible futures that you might encounter based on the changes that you are making to the system or changes that you are planning to make to the system. You can even try to optimize futures by trying to see which change is going to produce the best optimum result in the long term or near future when you're looking into the realization of different paths. Simulation modeling tools enable you to build digital presentation, or you can call it digital twin of a real system, and perform risk-free experiments. Basically, you're translating something in reality into its replication or like representation in a computer, and then you can use it for strategic, tactical, or operational level virtual experimentations. And compared to other methods like spreadsheets, optimization like linear programming and optimization, dynamic simulations are capable of capturing time, dynamics of the system, and also causal relationships that are built into a reality. And because of that, you can explain why things are happening, not just predicting them. And you also know that simulation could be visual if you want it, and which means that you can communicate and the results of your like hypothetical situations or solutions that haven't happened yet. So you can show it to the stakeholders, and also for you as the modeler, you can look into the results and verify and validate your model in a visual way as well. So this graph, as you can see, we go from the real object to the simulated version of it. You put all the data that you want from different data sources, and like a practical simulation ecosystem should be able to powerful enough, or like it should be capable to get access to different resources or data sources. And then we can both simulate the quantitative outcome of the system based on these inputs, and also visualize it, and then you will see the outcomes into the future. One critical portion of this like workflow is moving from the real object to the simulated version of it. So I put this like the red dotted line here because this is the most challenging part. And the usefulness of a simulation software is in helping you to translate this reality into a simulated version of it. The more tools and capabilities it has, it helps you more in your journey from the real object to the simulated version. Okay, so how we do this, how we go from the real world to the simulated version. So basically you have to abstract away from all the complexity of reality and put it into a computer. So there are different methodologies or methods that has been developed over years, like discrete event simulation or process-centric modeling, system dynamics. These techniques has been around for decades, and in early 20s, with computation power of computers get a little bit more sophisticated, we started to see visual modeling languages. Things became more visual and declarative, and you get to see better 2D and 3D animation. And at that point, also a new paradigm or methodology starts to emerge, which is called agent-based modeling or individual behavior, which focus on individual behavior of components or elements of the model. And AnyLogic at that point started to commercialize this approach. It was only mostly a research tool at that point. And later on, what AnyLogic championed, and still is the only true multi-method simulation tool, is building an ecosystem over the years that lets you to have access to all of these methods, these ways of expressing how your system works in computer, but under one roof. So when you are building your model, you are not limited to any of these specialized languages or methods. You can use them all under one roof and mix and match depending on what you need, which results in more natural and elegant model architectures. Although at the beginning, it might look like a little bit of learning curve because you now need to learn more languages. But after you pass that very brief, introductory learning curve, you get to use a much comprehensive tool set, which gives you a ton of flexibility in making your research or business cases more easy to model or deploy in the future. Okay, so now that we have like this overall idea of what simulation is and where AnyLogic, what type of technologies AnyLogic support, let's take a look at the software and AnyLogic Cloud very briefly. I have to mention that we will have vendor tracks and workshops tomorrow and on Wednesday that get deeper into the AnyLogic software itself and the cloud on Wednesday. So if you're interested, please join us tomorrow for the workshop. Tomorrow we'll also have a vendor tutorial for AnyLogic 9 if you're interested to see the roadmap of AnyLogic 9 and what comes next in near future. Look into that, and then on Wednesday, our development team will talk about AnyLogic Cloud and more detailed explanation of its capabilities. But for now, I just want to introduce you to this environment so you see, if you are new to AnyLogic ecosystem, see what we are talking about. So I'm going to switch to the software. Again, I'm not going to talk about how you build models or how this platform works, but what you are seeing on the screen is the development environment of AnyLogic. This is where you build models, and the workflow looks like this. So you have some graphical interface and some model building elements that you bring in from different palettes. And what these libraries or palettes are providing to you is like a more organized way of getting access to specific model building blocks. And then you drag and drop them into the model, and there are capabilities to add your own custom code on it, animation, and so on and so forth, with the help of all these elements that you find here. Again, this is not the topic that we are going to cover in today. If you're interested, please join us tomorrow at the same time. And you can find the links both in our AI and AnyLogic booths. Okay, so I'm going to just demo some models so you get to see different types of things that are possible with AnyLogic. I'm going to start with this autoclaved aerated concrete factory. As you can see, this model has a simulation experiment that I'm going to run. And at this time, AnyLogic compiles the model, and you will see a new window that gives you access to the model initialization configuration. What you see here is a custom build UI that lets you to select some of the settings of the model before you're running it, just defining scenarios. Let's run. And depending on what type of model you're building and your requirements, you can have 2D and 3D animation. You can see very high fidelity animations. And AnyLogic for the front end UI uses a browser-based approach for 3D visualization, 2D and 3D visualization. And we developed this proprietary approach to visualizing simulations on browsers, because it also goes pretty well when we want to run these things on the cloud or over internet on a server. And I will show you that. So the models that you're running locally on AnyLogic desktop, on your desktop, or on a server or cloud-based cloud providers will look identical because they're using the same browser-based UI. Looking into some of these, the model, you can see custom built feedback or dashboards here. Depending on what you need, AnyLogic gives you a variety of different ways of visualizing your outcomes or outputs. Here, things like utilization or amounts of time that you spend at different times, or time plots, some log, and time chart, so you can see at each point of time what a state each machine is on is available to you. So you can actually look into very visually see how your operation goes and get feedback. On top of these kind of visual feedback that you get, and it's up to you to decide what makes sense to be put in the UI, is you can definitely write all the outputs to any relational database, any Excel, like CSV, or even like any relational database that you want to connect to, and have some tabular information as the output for post-processing as well. Okay, so that was the first example. What is unique about this type of model, and I don't want to get into the detail here, is if you look into what is happening under the hood in this example, you will see that we use lots of kind of built-in fundamental discrete event blocks, but we also put them together to build custom blocks for a specific components of this model. For example, you have a crane, you can build your own custom built crane that is a combination of multiple components that comes out of the box with AnyLogic. Build that custom block and use it for future projects, or replicate it multiple times in the same model without the need to go back and design from scratch. Knowing that we don't have that much time, I have to go through this example a little bit fast. Accept my apology in advance. We will go through more thoroughly through some examples and explain them tomorrow in tomorrow's session. Okay, so the next thing that I want to show you is on top of fundamental model building blocks, AnyLogic also has lots of vertical libraries, many different vertical libraries for specific applications. And among them, there are material handling libraries, a library for conveyor systems and transporters, things like anything that helps you to move material inside a warehouse or inside the four walls, like cranes and transporters and lifts, for example, or elevators when you're moving things between different levels. Again, the other library would be pedestrian library that simulates movement of pedestrians inside a physical space, rail, road traffic, fluid, and these are the other vertical libraries of AnyLogic. So let's see a couple of examples of each so you see what is possible with these libraries. I start with material handling library and show you a couple of examples there. The first one is a fulfillment center, and it has pretty sophisticated conveyor system. The cool thing that you can explore in this model is the layout is configurable. So I can change like the number of receiving zones, for example, that I have here by playing with these levers. So even the layout and the logic of the model, or the logic that represents the environment that this model is working on is configurable with this approach. And running the model, you will see in 3D how this operation works. You have the capability to move around and see the operation from different angles, and you can see there is a pretty sophisticated geometry for and elevations for these conveyor systems. And you can build very interesting custom UIs for people to navigate through the operation. So you can make it like bars that people can click on and move around and focus on specific things. Or you can have one view that has multiple angles of the same operation. Okay, I want to show another example of material handling library, which focuses on the transporters. And AnyLogic supports two types of transporters. They could follow path, or which we call path-guided transporters, or they can just move in a free space. And this example that I'm showing you, these transporters or AGVs are moving in this environment in a free form, understanding each other's presence and also all the other obstacles in this environment. So you don't need to worry about how they find their way. They will find it based on the shortest path. If you wanted to guide them more, you can, but if you just say this is the endpoint, like a start and end point, they will figure out the shortest path between those 2 points, knowing that there are obstacles along the way. And similar to other type of models, you can build these custom user interfaces. And for this library, you can also see a density map of the presence of these AGVs throughout the simulated time and where was the congested areas, for example. Looking into the logic, what I want to put emphasis on is in majority or almost all of these vertical libraries, the declarative language that you're using to define the logic is a flowchart. So you're building models by flowcharts and sequence of like things that need to happen. So it's very in line with your experience with discrete event simulation and just step-by-step guiding of your 8 entities or agents throughout the flowchart. So very declarative, easy to follow, and visual. Okay, so let's move to a couple of other libraries. I will start by pedestrian library. Let's take a look at this and subway entrance hall. This is an example of pedestrian library that has been used extensively in lots of big scale projects. And one recent use case of this library that is very popular is for social distancing, because you can measure things like in 2D, you can see the congested areas where people are waiting. You can even build dynamic, you know, counters or some form of records of how many times they get into the personal space of each other. You can put some rules that they have to walk with specific social distancing, regulations. They follow those regulations and see how it's going to affect their movement. You can try different, work schedules or times to see if it can kind of manage the social distancing guidelines. And this also could be used for design of environments, evacuations, safety reasons, and things like that as well. There are many use cases, even for designing, like, let's say, shops, museums, things that you wanted to be in charge of the flow and guide people to a specific part of the layout. That is also another thing that you can test with this library. Okay, so next would be an example of road traffic. This is another library that comes with AnyLogic. By the way, everything that I'm showing now is going to be available. It is available as part of the AnyLogic professional license. So everything is there. So when you're buying AnyLogic professional license, all of these packages are come with it. Even if you have a university researcher, you get access to all of these. If you're using the personal learning edition, which is free, you might have some limitations on some of these extra vertical libraries, but still the limitations are very generous, so you will be able to test all of these examples that I'm showing right now. And this is the road traffic library, and similar to the other one, you can see the density map. You can also put the camera on top of a specific agent and watch the movement from their point of view if you want to. Okay, so now that I've showed you some examples of vertical libraries, I want to show you two examples of multi-method modeling. These are pretty simple ones just for the demo purposes, so you see how this concept works, but if you are interested, there are more sophisticated examples in AnyLogic repository to look at. So the first one is a supply chain example. What you see here is a combination of all three methods. So agent-based modeling, discrete event, and system dynamics. How that works is the distribution centers and factories on these models are agent, but the internal of the factories, and also the trucks are agents here. Internal of the trucks are modeled with a state chart with a specific construct that we support in AnyLogic, and lets you to easily define individual level behaviors for your objects or agents. But for the these manufacturing centers, which are these red icons, we use for their internals, what is happening inside the manufacturing center. We use discrete event and system dynamics. And basically what I did is I clicked on Chicago and I went inside Chicago. So what you're seeing here is a process of how this manufacturing center is processing incoming orders, which is modeled by the discrete event process. And you see the production is like a continuous production that is modeled with the system dynamics. So you can see that you can mix, and these two constructs are both inside an agent. So you have a model that is a multi-method one with a combination of all of these methodologies. And basically, AnyLogic doesn't put any limitation on the way you're using these different methods. So if you need them, you can use it based on what makes sense for each component at the global level, or for the architecture of your model to make things more scalable, if that makes sense. And lastly, I wanted to show you an example. Like, this is the example, simple, but demonstrates again another way of combining or building models with different methodologies. You have agent-based approach of some form of epidemiology model that you see like a flu being passed along people in a community, but depending on how many people are sick, there will be some request for use of a treatment center or a hospital. And then we can gauge how much capacity we need in our hospital to deal with the demand that comes from this epidemic or pandemic in this case. So I just wanted to mention that like these type of models could be easily done with AnyLogic. And the point here is, so this part, the epidemic and like the flu, infection being passed between people made sense to be modeled with agent-based model at individual level. We did it with that approach, and the treatment process of how many resources we need for the treatment made sense to be modeled with a flow chart, as we are usually do in hospitals or process-centric systems, and therefore we modeled that portion with a discrete event model, and it all makes sense. Okay, so I spent too much time here. I want to also mention that we have AnyLogic Cloud, which we will talk about on Wednesday around noon. But what this platform can do for you is it gives you this very easy to use execution or runtime environment that you can easily, with just a couple of clicks, set up your simulation inputs and outputs and upload to that platform. And then here you can go to your models and run them and build experiments here, run multiple simulations with the computational power that comes from the cloud, or share your models with others. And one thing that I want you to kind of see here is that what you get on the cloud side, things that I'm running right now on a browser, is identical to what you see and get access to on the desktop version. So there's no limitation, they're completely identical. It actually gives you a couple of more features like building these experiments on the cloud, and you can build very robust dashboards for your customers or end users, and you can easily share your models. But this, again, needs more time to get into the details. If you're interested, please join us on Wednesday. Okay, so now let's get back to the main topic of this presentation, which is simulation and artificial intelligence. So just some conceptual ideas about where simulation is different from artificial intelligence. The main, like if you wanted to kind of say everything in a very concise way, is simulation uses causation versus machine learning or AI that is mostly built on uncovering correlations or relationship between different features in the data that you record historically. So from the point of like a modeler, a simulation modeler looks into the real system and tries to uncover the causal relationships that he or she can find there. And it has to be in contact with the subject matter expert, learn about how that system works, and then try to model those rules into the simulation. Versus a data scientist, again, this is a pretty oversimplification of the process, but just the gist of the idea. For a data scientist, the focus is on the data, and the assumption is all the relevant information that we can extract based on our objective is kind of inside this data. So all the data scientist needs to do is to get that data and try to uncover those information that is inside it. And theoretically, the data scientist does not need to know that much about the real system. They can just focus on the data and uncover the relationships between different features. And if I wanted to kind of summarize some of these things, simulation modeling is great in capturing the dynamics of the system and stochasticity or randomness. You can uncover all the underlying rules and interdependencies because you know how things work. And you can also explore novel scenarios into the future, things that have happened in the past. You can even go into the past and do counterfactuals, try different scenarios in the past that haven't happened. These are things that you can't do with data-driven approaches. And you can also visualize very easily in simulation because you're simulating the actual operation. And you can build other experiments on top of a base simulations like Monte Carlo optimization and make decisions or make recommendations based on running simulations. In contrast, machine learning, there's no need to uncover the actual rules or implicit rules of the system, but it makes things more fast because all you need is data if it's available. And sometimes they are pretty effective in providing very predictive futures, and they can very effectively uncover historical patterns in the data. And with they used to be much more cumbersome to do with AutoML platforms and all the new packages that are coming out every day. Building those models becomes easier and easier by the day. So definitely ease of use is a good point for just machine learning or AI tools. Okay, but then we are going to focus on the intersection of these two. And before I get to the point of explaining why this intersection is important, I want to put more emphasis on one unique aspect of simulation modeling that makes it extremely unique and to some extent something that you cannot replace in a AI context. And that is the unique feature of simulation which lets a modeler, a human, to put its understanding, its causal inference of how the system works into a model. So in other words, in an ML model, the way that they work right now, they are just looking into a data and try to uncover some form of correlations, extracting all those correlations. But there is no way to infer any causal relationships from the data. You can get very close when you're having really good models, but absolutely they don't even claim that they can uncover causal relationships. In contrast, simulation on its core is built based on a human, a modeler, using its own understanding of the system and extracting those causal relationships. So that unique component that the modeler has been put into the simulation is the core unique feature that adds a lot to any other ML solution that will be mixed or work together with the simulation. So this is what I wanted to put emphasis on. This is the core capability that we are looking for. So knowing that, how we can use these two different approaches to uncovering knowledge from looking into existing or systems is possible. So yeah. We just to make things simpler and easy to digest, we tried to categorize these intersections into 3 different categories. And you can do it in different ways, but we feel this is a pretty easy to understand categorization. We think that the first case could be generating synthetic data with simulation and then use it in some shape or form with other AI solutions. The second use case or category of use cases would be using simulation as the learning environment for reinforcement learning. And the third case is using simulation as a test bed for AI components. And for each of these, I will get into more detail and explain what are the different use cases, and Tyler will show us actual implementation of these things and how you can do it today in AnyLogic. Let's start by generating synthetic data. I just put together like 5 cases so you can have a more visual or a concrete understanding of what I'm talking about. So as you know, the data that you are generating from a simulation is not real data. So we call it synthetic data. The first case would be for ML researchers, people who are developing new novel ML algorithms or network architectures for deep learning, things like that. They want to test these models to see how good they are. And the challenge becomes how we can have some form of objective, noise-free data, and maybe unlimited number of them, or unlimited number of labeled data. So how you can get that, it's almost impossible to get something like this based on your specific needs from real world, or it could be very expensive or cumbersome. So in contrast, you can easily build a simulation model in that context and generate unlimited number of clean labeled data and use that for testing your ML algorithms. So that's just for researchers that want to test the efficacy of their models. The second use case is you have some real world historical data, but that's not enough. You can simulate like a counterpart version of the reality and generate some synthetic data and mix them together to basically enhance your real data with synthetic data. The third is using the simulated data or synthetic data to build a proof of concept for somebody else. Basically, the idea is like this. So you are an ML engineer, and you know that you can do a great job with this specific type of data, predicting some very specific thing for, let's say, a customer. But you don't have the data. So it's a matter of chicken and egg now. So you don't have the data to prove that your ML model will work and have lots of predictive capabilities. So what you can do instead is say, okay, to prove the usability of ML solutions, I can build a simulated version of your operation and treat those synthetic data as if they were real data and show you that with this synthetic data, I can provide lots of predictive powers, which proves my point that we can go back to your real system, invest in time and money needed to gather the real data, and then build a more representative ML solution. Case 4, approximating the simulation models with ML models. This is a very generic scenario in case you, for some reason, we know that like running simulations is not easy, and specifically if you have a really huge model that needs a ton of computational power to run. Maybe you wanted to have a function that approximates the entire of simulation. So you just put some inputs and it gives you an approximation of the simulation output. It's not going to be perfect, but it gives you some useful information. And a subset of this would be, let's say, when you wanted to deploy a simulation on an edge device, a device that has very low computational power. So instead of trying to put and run a simulation on an edge device, you can build a approximated version of the simulation with, let's say, deep learning, and you have a trained neural network that then you can deploy on an edge device, and that device, let's say a controller, now knows how to control things based on some input, and it gives you the output you need to control your system. Okay, from this point on, you will see that I switch between light colored or background slides to a darker themed one. And the reason that I did that is to give you a clear distinction between a concept and implementation. When I show you a dark theme slide, means that this is the implementation of the ideas that I talked in the previous slides inside AnyLogic. These are the technologies inside AnyLogic that helps you to deploy or build things based on the ideas that I talked about in the previous slide. So first one, as you know, we talked about different ways of using synthetic data, but how we can use AnyLogic to kind of build this synthetic data pipeline. The first thing is just as you know, this is very similar to the regular use case of simulation. You just output some data and you basically use that data to train an ML model. So you can do it based on built-in databases of AnyLogic, write it to that, write to external data sources in AnyLogic, or you can make it more like a live loop, not for reinforcement learning, but just to get the data, generating the data first, do the ML training, and have it in one go, instead of first writing it out to a database in an offline mode and use that as a proxy between your simulation and the ML. So in the second, these two with AI, Cloud, and Alpine, you can do it in one workflow. You can say, this is the setup, run the simulation, you get the data. As the data is still there, you do the ML training, and then you have a trained model. And you can do the same thing with Alpine, similar to AnyLogic Cloud and its API calls, but in an offline mode. So now Tyler is going to show us an example of a model that he built as an approximation of a real simulation example. And he used external databases. So he wrote out all the data and he trained the model. So with that, I'm going to stop, and Tyler is going to show you that example.
Thank you. Okay, so for the model, I used the consumer credit model, which is one of the default AnyLogic models. So in this one, clients are coming into the system and trying to apply for some credit, either online or in office. And then they go through a process of consultation, and their application goes through various different resources. And at the end, there is one of three results that can happen. So the two primary ones is they can either succeed and get their credit approved, or they could fail and it could be rejected. The other case is that in some situations throughout the model, so if I scroll down to the flow chart, some of the queues have these timeouts. So in case there's too high of arrival rates, or the resources are in short supply, customers will get bored or impatient, and then maybe choose a different bank to try to apply to. So in those cases, they'll end up timing out and having no decisions. So what was modified from this is that at each decision point, it outputs to the database a couple of details. So if I open up this, so for each client that comes through the system, it logs some of their personal attributes, which are inside the client agent, such as their agent salary, some flags, their credit amount, but also some attributes regarding the state of the system when they had first arrived. So the number of idle resources and the sizes of some select queues. And then here we have an outcome, which is a value either 0 if they were rejected, 1 if they were approved, or 2 if they timed out. And so this was using kind of built-in features of AnyLogic, outputted to a, if I go back to here, so this is inside the model folder. It outputs to an outputs Excel file. If I open up, this is a preview of it, so the same information. So then external from AnyLogic, there was, using Python, there were 2 different regression models which were trained. And the point of these was to predict based on the input data, what the different outcomes would be. So there's one that predicts whether or not they timed out or didn't time out, and then one that predicts whether they succeeded or if they failed in getting their credit. And so this was kind of split into 2 different models. And so this just uses the sklearn Python library and kind of a basic logistic regression to train that. And for both of these, they were saved as pickle files, which essentially means that they could be reused and recalled whenever you want to retrain. So one thing I'll note is that while I used the AnyLogic built-in database and exported to an Excel file, you could, as an alternative, upload the model to the cloud and then run the model here, and then using let's say the Python API, you can retrieve the results from running, hundreds and hundreds of different experiments with different scenarios, and then for each of those, getting the results for each of the clients that went through the system. And so the AnyLogic Cloud has a very extensive documentation for APIs, both for JavaScript, Java, and API, allowing you to not only get the outputs from experiments, but also create simulations or parameter variation experiments for models that are uploaded to the cloud. So with all of this, we have our two regression models trained, and they could be put, well, there's a few different things that you can do with it. One is an example of case 4, where you're approximating the simulation models. And I'll explain this and go into detail a little bit more in the following sections, but essentially you can shorten the model down to a simple decision point, and using that regression model can, based on the arriving clients, predict in advance whether or not they have a positive or negative decision. The other thing that you could do possibly is take the timeout regression model and maybe add a indicator or a checker operation at the start, so that it would predict whether or not this client may time out. And then as a result of that, you could then have some actions taken, such as making sure that there's more consultants that are working on that given day. So from all this, you could take that synthetic data and then manipulate it inside of Python or any other language and use it however you want. So with that, I will turn it back over to Arash to go over the next section.
Thank you so much, Tyler. Okay, so now we are moving into the second category of use cases, and that would be using simulation as the learning environment in reinforcement learning. And we spent a lot of time building connectors with our partners, and we developed multiple other technologies in case you are researchers that you wanted to try these things, build your own RL setup from scratch through connectors that we developed. So we'll talk about all of those in a minute. But if you're new to the concept of reinforcement learning, the idea is pretty simple, is that so if you wanted to teach something to an entity, let's say a dog or an AI agent, so it doesn't matter. When you wanted to teach it, there are different approaches to do that. But one way is just by trial and error. Let's discover all the possibilities. Let's play over and over again. And over time, by giving enough incentives or a good reward system, that learning agent, or let's say a dog, will learn what would be the best way of acting or taking action in different scenarios. So that's very simple, just trial and error and learn from your mistakes and successes, right? So that's the main idea. Where simulation comes into play is we are going to, with simulation, provide this learning environment, the playground for the AI to play with and learn from. If you wanted to look at it from a different perspective, you can think about regular simulation. The entity that learns from the simulation is a human. So you experiment with the simulation, you run different simulation with different inputs, and you as a modeler or end user of the simulation get some feedback and kind of extract the information from the simulation and then say, okay, so I've learned that these are the possible futures. This is what I am proposing as the action. But in the case of reinforcement learning, you are not in the loop. An AI agent will communicate with the simulation depending on what is possible to be the levers that are available in the simulation model. It tries to play with all of those levers and learn what is the optimum or near optimum way of taking action in the simulated environment to control this environment in an optimal way. In another way of looking at it, a simulation, a conventional way, is something that is complete on its own. In reinforcement learning, simulation is part of this learning setup. So it's not going to be used on its own. If you're running on its own, it just doesn't give you any useful information. It is meant to be built to use as a learning environment for the AI agent. So when you put them together, you let the AI agent learn from the simulated environment. Then at the end, your deliverable would be this trained AI agent, which is like an expert now in controlling that system. And to be able to do that, what needs to be changed in a regular simulation is a way of communicating with this AI agent so it can look into the system and see what is happening, or actually get some reward from what it's doing. And then there should be something in your model that lets this AI agent to take action. So there should be some levers accessible to this AI agent to implement its actions or what he wants to try to learn in the environment. How you do it in AnyLogic, we developed 3 options for you. One is AnyLogic Cloud with its interruptible cloud API. So what you need to know is this cycle is a pretty computationally expensive cycle. You need to probably run hundreds of thousands of simulations, so it matters when you're running these simulations, theoretically, depending on how complex your models are. But AnyLogic Cloud gives you this backend runtime environment that lets you to use the computational power of the cloud. And through that, those API calls, you can run multiple runs of the sim or the simulation and kind of channel back the feedback and connect to the AI agent and let the reinforcement learning loop to happen. So this is something that comes becomes available pretty soon, early 2021. The second option is we work with our automated RL partners, Pathmind and Bonsai, in the past 2 years. We started this and they there are lots of improvements happen in both of these platforms. So you can look into each of them, and Tyler will demo briefly both of them so you can see how they are different from each other, but they're both great automated RL platform. Depending on your need, you need to look into the nuances and choose the one that makes more sense for you. But what we recently added to AnyLogic 8.7 is this new reinforcement learning experiment that is accessible to you in all different types of AnyLogic, from personal learning edition up to professional, meaning that if you wanted to test these platforms, you can use any of AnyLogic versions and do so, knowing that, so if you are using PLE, you will be limited by the limitations of PLE. So it's obvious, but if you wanted to test these platforms for educational purposes or for research, you can, and because AnyLogic university researcher does not have that much of limitation, so you can build almost anything you want and use it for RL research. And the third case is a library called Alpine that lets you to build something like this. It's similar to AnyLogic Cloud API in a sense that so you are not using an automated RL platform. You have to set up the entire RL setup yourself, but the connector is available to you to connect your Python code or Python setup, let's say based on OpenAI Gym, workflow with the exported model with Alpine. So this would be an offline version when you're running your models on your own machine. This is an online version when your models are run on AnyLogic Cloud. And this would be a case when you want to automate the entire process. You don't want it to basically curate your own RL algorithms and setup. Okay, so now we know that we have these 3 options. Tyler is going to briefly show us a little bit of the 2 option 2 and option 3.
Thank you, Rash. Sure again. Okay, so starting off, we will take a look at PathMind. So, and for this, we're going to be using the supply chain model, which was, so this is one of the example models, part of one of the tutorials that PathMind provides. It's part of their platform, which is modified from an AnyLogic model of the same name. And so in this model, you have, it's a simple supply chain with a retailer, a wholesaler, and a factory. And then there are inputs to the model or values which allow you to manipulate what the inventory level policies are. And so the goal is to manipulate these in such a way that minimizes holding costs, which increase with larger inventory sizes, and then also reduce wait times, which happens as the inventory levels decrease. So there's kind of a complex interactions happening here between the three facilities. So to use it with the PathMind platform, there's a custom PathMind helper object that you add to your model. So this object itself is found within the palettes. So within AnyLogic, you can add custom libraries. And so both PathMind and Bonsai offer their own custom libraries that you add to your AnyLogic development environment, and then you can then drag these objects out and configure them. So for PathMind in its object, there are fields for the observation. So this is what the AI will be seeing as part of the training. There are reward metrics that you specify, which are used to use as part of a reward function to judge the how well an action did. And then an implementation of an action in addition to kind of the dimensionality of it. So in this case, our observations consist of different attributes for the retailer, the wholesaler, and the factory, along with the model time. And then also the actions consist of modifying those inventory levels, both the lower and the higher one. So with all these defined, you add some code to trigger the action when it needs to happen. And then as Arash was explaining, you have the RL experiment. So because PathMind has all these fields defined within their PathMind helper, you could leave all this blank. And then there's an export to PathMind button at the top. This will compile and zip up your exported model. And then after you paste in an access token, we'll automatically upload it to the PathMind platform. And you'll be brought to a screen that looks roughly similar to this. So here you have a few different boxes. This is where you define the numerical reward function, which is used to judge how well an action did. So, and how they're calculated within PathMind is typically by comparing observations before and after an action. And so in this case, our numerical reward function is based on the difference between the daily cost and the wait time. And then you have these access to these variables. Additionally, on the right here, you see all the observations that were included. And if you want, depending on, maybe you added too many observations or you want to try a subset of observations, you can click on these checkboxes and then the AI won't see those observations as part of the training. And then you go ahead and start the training, and when it's done, it will look something like this. So when training is finished, you have a few different graphs here. Here it shows your simulation metrics, so those values that were added. And these are all shown over the course of the AI training. So you can see that the inventory levels over iterations decreased. And then same with the mean daily cost and inventory levels. These are then displayed down here for convenience. And then there's also another chart to display how your reward was over time. So you can see that the reward is increasing. So now that this training has finished, you could export the policy, and it downloads as a zip file. Excuse me, Zoom is in my way. So if I go into the AnyLogic model folder, you can see that I've already added these policy files here. And then what you could do is you could test the implementation of those policies by going back into the PathMind helper inside your AnyLogic environment. and then changing it to use the zip file for your policy. And then when you run the model, you'll be able to see the impact of the simulation as a result of that. And so, in any case, so they also provide a Monte Carlo experiment as part of the model that they provide, which is downloadable from their website. And then, so I want this one. So there it does that. And then if you run the Monte Carlo, you can compare the results of the AI policy that was trained versus an optimization, which was performed using the AnyLogic OptQuest. AnyLogic's built-in optimization engine, which is OptQuest. So here you can see that the levels will now fluctuate by themselves. And there's this event here that's firing at a recurring interval. And so every time it's this event is firing, it's taking a look at the observation and changing the action to natively adapt the system so as to, in accordance with what the training had provided. So switching over to the Bonsai platform. For this, we'll be taking a look at the activity-based costing analysis model. So in this specific model, we have products which are arriving to a factory floor, and they see two different types of resources. They get delayed in machines for some amount of time, and then afterwards they get conveyed to an end point. And so as part of this process, there are costs associated with each aspect, from idle costs to waiting costs, processing costs, and conveying costs. And the ultimate goal is to reduce the overall cost per product. So originally in this model, you can manipulate these sliders so as to play around with the original simulation and see what happens if you increase the machine time. If you increase the machine time, there'll be a backup of products eventually. Same if you decrease the resources, and all of this is adapting to the overall cost per product as the simulation advances in time. So the goal here is that based on a variable arrival rate, we want to configure these other 4 sliders so as to minimize our overall cost per product. Similar to Pathmind, there's a Bonsai connector object, but in the case of Bonsai, it's used exclusively just for your access tokens. You define the observations and the other attributes inside of the RL experiment. So here we are listing the various different fields that we want the observation to be consisting of, in addition to implementing those. Same with the stop condition, the action, and also the configuration, which is a kind of the starting condition for the model. So when each episode starts up, we'll use this configuration for that simulation run. So once this is all configured, you then use the export to Bonsai option. This will save itself to a zip file. And then to use it on the Bonsai platform, you'll first need an Azure account, and you'll need to be familiar with that and how to get that set up. And then you can, under it, add a simulator, choose AnyLogic, and then upload your model. And so then what it will do is wrap your simulation model in a Docker container, and then it's able to be natively used inside this platform. So for the Bonsai platform, it has its own language for machine teaching called Inkling. And Inkling is a declarative language that's specifically used for AI training. So it kind of abstracts away from the lower level machine learning code that you would need to implement otherwise in Java or Python. So here, after you've uploaded the simulator, it kind of detects the various different fields. You can actually create a brain from this. And then at this point, you can kind of define the ranges. Similar to Pathmind, there's a mechanism to kind of take a subset of the observations you passed. And then there's definition of the action and the configuration, some auxiliary functions. And then at the very end, there's the reward function, and then there's this graph. So in this graph section of the code, this is where you're declaring how you want the lesson plan to be for the AI, for the brain to learn with. So what's unique about Bonsai in this case is you could set up multiple lessons to kind of build the learning process incrementally. So at the start, you could introduce conditions which are easy to learn from, and then slowly advance that to more complicated scenarios, and introduce various different lessons for learning different components of your system, which is especially important if you're not wanting to try to throw everything at it and try to have it learn everything at once. So when you click on train, it uses spins up multiple instances of your uploaded simulator, and then at the very end, you'll be able to see the graph, which is taking some time to appear. And then what you could do afterwards is you can export the brain. So when you export the brain, you're able to wrap it in a Azure web app, and this allows you to have a endpoint where you could use HTTP requests to predict what the output should be based on a given input. So for example, I could say, test this out. If the arrival rate is 0.65, it will tell me what my actions should be for that, based on that input. So once you have a URL composed for this, you can then go back into AnyLogic, and inside of your Bonsai connector object, you could paste in the exported brain address, and then it will natively query that exported brain. So at this point, what you could also do is take this and upload it to the AnyLogic cloud, which is what was done here. So if I go to my models and this, and so now I can run this activity-based costing analysis, and this already has my exported brain address built into it. These sliders are now disabled because they're controlled by the brain. And so now I can change the arrival rate, and you'll see that these change on their own based on what the result of the queried brain was. So that's kind of a short summary of Bonsai. So lastly, we have something that was briefly mentioned before, which was Alpine. And Alpine is a custom Python library that allows you to run your exported AnyLogic models. So for this example, I'm going to be showcasing it with this very, very simple model that uses the road traffic library. So in this model, there's cars that are coming from opposing directions, and each opposing direction has its own arrival rate. And so there are endpoints functions in this model for RL-related actions. I'll just point that out for now. So with Alpine, it will be a Python library that you can import using pip. And so you'll just import it. And so what it allows you to do is connect, like I said, to an exported AnyLogic model. So here I'm specifying it's the model.jar file. You can create multiple instances from that model.jar. And so each instance will be its own unique simulation run. Here you can see that it prints out various different attributes. So using this library, you have access to the parameters of the model, any Java variables, all the various different functions, and analysis objects. And so whenever you decide to reset the run, if you're using a random seed, this prints it out for you. And this is useful because the server itself, which is running behind the scenes, is Java-based. If you wanted to recreate this instance of the run, you could just paste the seed into your AnyLogic simulation environment, or the development environment, and have these same results. as you kind of saw from the pop-up, after resetting it, I ran the model, advanced it for 1 hour in 8 increments, and then looked into the model to get the built-in data sets. And so this is what popped up using the matplotlib library. So this is not only useful for just running your AnyLogic models within Python, but also for reinforcement learning. So within the Alpine library, there's a class called ALENV, or AnyLogic environment. And this is a subclass of the OpenAI GIM class. And so what this allows you to do is have a custom GIM environment. So in addition to connecting to your model as with before, you can create this new environment and passing in the names of the functions inside of your AnyLogic model. In this case, get observation and do action, along with the dimensionality of it. The time step in between actions, the terminal function, and the reward function, along with how many arguments it has. And so both the terminal function and the reward could either be within the AnyLogic environment or within the AnyLogic model, or it could be within your Python environment as well, if you wanted to later modify that. So with this AL environment object, this works exactly like any normal, kind of quote unquote normal GIM environment works. So if you have libraries such as TensorFlow or PyTorch, or in this case, stable baselines, you can train a AI using your environment that you had created and pass it just like you would like a carpool model, for example. And so from this allows you to do whatever sort of training that you are normally familiar with in a Python-based environment. And so the other advantage is that each of these instances are running in their own separate thread. And so what this means is that you can run multiple ones at once and kind of expedite the training in that way. So at this point, the learning process is starting. We're not going to sit here and wait for it because it takes about 30-ish minutes. But once this is done, this is saved as a policy that you can use just like you would any other policy within Python. So with that, that is a brief overview of the options as far as training reinforcement learning agents. I will turn it back over to you, Arash, to go over the next case. And you're still muted.
Thank you, Tyler, for mentioning that. Just a recap of what Tyler showed you. He showed you these two workflows for Pathfind and Bonsai. These are automated RL environments, meaning that all you need to do is to make the connections, basically defining the configuration, action, and observation spaces, and then upload it or export the model and upload it to Pathfind and Bonsai for that automated RL to happen. In case of Bonsai, Tyler showed you that you need the Inkling code as well, just to set up the machine teaching environment as well. But majority of the work is automated in these platforms. The third option that Tyler showed with Alpine, it gives you the connection, but the RL setup that you need to put together based on OpenAI GIM workflow or anything that you want to do, custom-made building your network and how you use the data that you get from the simulation to train your AI agent is up to you. It's mostly for more advanced users or people who are, want to have more control over all the setups of their learning setup. With that, let's move on to the third category of use cases, which is using simulation as a test bed for trained AI. Let's take a look at some of the use cases that we identified so far in this context. The first case is using ML models, a model that is already trained, and put it inside the sim as a substitute for an input in an original simulation. For example, Tyler will show you an example that you have, instead of having a distribution in a delay when you wanted to capture the amounts of time that an entity or agent waits in a specific block, you can use a distribution. Say it's a random distribution with a triangular shape. But instead, you can say it's based on a predictive ML model that we train based on historical data. And if you're using agent-based modeling, you can actually associate it with the characteristics of the agent that comes and needs that prediction. So it becomes super useful when you're building multi-method models, which are the combination of agent-based modeling and discrete event simulation. For case 2, we are using ML models to approximate the behavior of a specific component. Just imagine that, so as you know, in this type of general purpose simulation tools like AnyLogic, you are not getting deep into the physical level of, let's say, how a chemical reaction is happening inside a block of concrete as you move it on a conveyor, right? So you don't see those type of things. We are not getting into physical level things. But let's say for some reason you wanted to capture something like that at individual level, and that is not something that you can simulate, but you can approximate that, maybe a character like a moisture content, with an ML model. You put that ML model inside a component, and as it moves, if you need to know what is the current moisture content here, you can ask it from that object, but the response that you get is not simulated. It will be predicted from that ML component or train ML model that you put inside the object. Case 3 is using deployed ML models in the simulated environment for a more accurate simulation. Meaning that as we go into in reality, more and more ML or AI solutions are being deployed in reality, it becomes more and more relevant for us as simulation modelers to be able to incorporate those components into the simulated versions in an accurate way. So if we go to a bank and they are already using 3 ML models to maybe sort some of their transactions, and you wanted to build a simulation out of that, so now you have to have some version of that ML incorporated into your simulated version of the operation, which is, you need that kind of capability in your sim tool to be able to do that. Case 4 is testing the impact of AI solution on the system's overall performance. So what is common right now in the data science community is to focus on a specific component and use data there and test it based on some test data and say, okay, show me the accuracy of like my prediction based on the portion of the data that I put aside for testing. And then I say like, yeah, this has a really good prediction power. This is a good model to predict, for example, demand for my store or this specific shop. Okay, so you have that. But the problem with that is this is just one part of a bigger picture. And if you wanted to make really good decision and test the result of changing the accuracy in your predictive models, you wanted to put it back into an overall system and see, now that I know more about my, for example, demand, and I can predict the demand in a more accurate way, how it's going to affect my operation. And that's where embedding these ML or testing these ML solutions inside simulation comes into play, so you can look into the overall picture and make more holistic decisions rather than just focusing on components. Say, I improve this component, but I don't know how it's going to affect the overall system. And people who are experts in process-related optimization, they know that the bottlenecks are always shifting and moving and are dynamic. So just getting rid of one bottleneck is not going to always improve. Sometimes it might be even makes the overall performance worse. The 5th case is visualizing the math. Let's say you are people who are doing data science work and providing machine learning solutions. Those are basically all mathematical models. So showing a result there is almost lacking. So you can do some, graph to show like that you're improving some metrics, but showing that it actually has some improvement on an overall system is something that you can't do only with ML. So you can put it inside the simulation, and the visualization capability of the simulated environment would be a very compelling medium for the end user to understand the usefulness of those ML components. And case 4 is what Tyler actually showed a couple of times in the previous section. When you are done with your RL training and you have a train policy, you can put it back into the simulation and say, okay, so now let's test this policy. Let's see how good it performs in controlling this system. And instead of first deploying in real world and see how it behaves there, but you can actually do some tests in the simulated environment that it's been trained on to make sure that at least it is controlling it in a desirable fashion. Okay, how we can incorporate ML models or embed them into simulation, or basically using simulation as a test bed for trained AI. The first option is when you have these trained models on any of these, like let's say, platforms like Azure, Google, GCP, or AWS, or any of these automated ML providers, or like big tech companies that provide you these platforms to train your models. They usually give you some form of endpoint to like a web app, let's say, that lets you to talk or get results from those trained models. And AnyLogic is a Java environment. Through API calls, you can easily call them and incorporate those trained models into your simulation. So this is pretty straightforward, but the second and third option is something that we built with collaboration with our partners or internally to give you more tools. So the second options, we partner with H2O.ai. They have this very unique automated ML platform that is very popular among the data science community called driverless AI. And we kind of documented and built a very easy to follow workflow for you if you're using their products, so that you can incorporate your trained AI solutions into AnyLogic and simulate them as part of your model. And the third option is a connector between AnyLogic and Python, which lets you to get access to any Python packages or any Python code or algorithm that you have in Python. On top of that, this could also be used for getting access to any trained ML model that you have on your machine locally, and get prediction from those trained models and add it or embed it as part of the simulation moving forward. With that, Tyler is going to show us an example of H2O.ai model being driverless AI's workflow, and the third option, which is pipeline.
Thank you, Arash. So like Arash had said, driverless AI is a platform by H2O. And it allows you to upload data, and it can process it and use advanced machine learning to identify the features and the various different trends. And when you have a file, or when you have a trained model which is adequate, you can export it as what's called a Mojo file. And so in this case, we took the product delivery model that Arash was showing before and trained a few different machine learning models based on that. So here you can see within my model folder, I have this runtime jar and then some Mojo files for two different attributes. So there's one which predicts the temperature in various different cities based on the time of the year. And then also another one for predicting changes in order amounts based on with or without a COVID effect implemented. Option to choose these at the startup, and when the model starts up, it starts running. So it's utilizing these trained Mojo files that were trained in H2O, their driverless AI platform, and so you can get various different statistics on it. And so you could change these on the fly to either use kind of random inputs or utilize those H2O forecasts. And so from this, you could see how the model changes with or without over time. And then there's also additional sliders, which allow you to kind of dynamically configure the rate, which kind of will have an impact on the predictions that are made. So that is driverless AI. And then finishing up with Pipeline. So Pipeline is a library for AnyLogic, which allows you to, you can add to your development environment, which allows you to connect to a locally installed version of Python on your system. So it uses Python in the libraries that you have on your system as well. In this case, this is the consumer credit model I was showing before. And so there are functions to kind of import a local Python file. And there are also functions to convert AnyLogic agents to JSON, which is JavaScript object notation. And then it can query that Python function using Python, which kind of loads that those regression models that I was showing before. And so from this, you can immediately get results, based on the known inputs for the clients that are coming into this model. So the inputs to this model are still the same, but now you're able to see kind of approximate the simulation, using these regression models that are within Python. And so in this case, I'm using Python 3.6. And this library itself is available on a GitHub page, open source, which I will show shortly. But kind of a more practical example is a simple hospital model. So in this model, there were two different data sets that were taken from online. And you have the sources listed here. And there were two different neural networks that were built. One was to predict the arrival rate of patients to a hospital based on the previous data. So over time, it looks at the past arrival rates. And then once patients come into the hospital, they have various different attributes. And then this other neural network predicts their length of stay. And so the variable parameter is the capacity of the hospital. So similar to the epidemic model Arash was showing before, you can manipulate this in various ways and see how the number of people that are queuing for the hospital are changing over time. Top graph up here shows the daily arrival rates, whereas these other ones show the other results of the AI models. So you can see little brain icons indicating where in the model that these files are referenced. So in the case of Pipeline, there's a GitHub page for the AnyLogic Pipeline library. So with that, I will turn it back over to Arash to finish us off.
Okay, thank you so much, Tyler. Going back to our three major categories, this is just a summary of what you saw there. As you realize so far is we are providing different ways and approaches for implementation of each of these categories. And we intentionally are doing this because we are aware of the fact that people have different workflows and needs. So we are not focusing on one specific technology. We know that some of you may want to use cloud runtime environment. Some of you prefer to do things for research, maybe offline. Some of you might have offline computational power that is good enough. Some of you prefer, automated platforms like Bonsai Pathmind for reinforcement learning or H2O for training your ML models. And we are understanding that you might want to work either in Python or Java based on what your language of choice is. And we are providing this ecosystem. So regardless of how your workflow will look like, you will find something that satisfies your requirements. And we are keep doing this. So we are keep looking into anything else that can add to this ecosystem. So the time you are investing, so we know that the time you invest in learning simulation or a specific ecosystem like AnyLogic or any other tool in simulation is very valuable, and it takes some time to master these technologies. And we really value your time, and we want you to keep getting access to the latest and greatest technologies in AI. And we are working with multiple partners to make sure that we always have the latest for you available. At the end, I wanted to show you a couple of resources if you are interested to follow up on some of the things that we showed here. Everything that you need is available in AnyLogic.com website. First, if you wanted to download the software, you need to go to the download page. A personal learning edition is a free one that you can download and have perpetually. It's pretty generous in its limitation. University and professional are the paid versions for research and professional. They are pretty similar. The licensing agreement is different. You can only use this for research. So please feel free to do so. And these two also are available to you for 30 days in an evaluation mode in case you wanted to test them before purchasing it. For more resources about AI, please go to AnyLogic.com. Again, features, artificial intelligence, and you will find landing page for Bonsai, H2O.ai, and Pathmine. Inside any of these pages, you will get access to all the required material that you need to find, like the models that we build with these partners. And if there is a video tutorial or a webinar, you can get access to it as well. Under resources, you are also finding other things like white papers that are might be of your interest, books, video tours of previous webinars about AI and panels like that, things like that. And also, I highly recommend you to take a look into our training schedule. Join us now. Majority of trainings are online, so definitely it's a good time to join us regardless of where you are. So there's no need for travel. Yeah, and with that, and one other thing, in case you are interested to inquire about anything about the software itself or other questions that you might have about the capabilities, you wanted to have a custom demo, please feel free to go to the company and look into the contacts and also partners in your region to ask for a more a specialized demo based on your needs. I'm also going to put this QR codes on the screen in case you wanted to look into AnyLogic, cloud, and the AI landing page, which gives you access to all the other resources. And with that, I'm going to end this workshop. Thank you so much. I really appreciate all of you that joined this workshop and stay till the end.